In this session, we are going to learn about an important concept known as Miller indices. As of now, we have seen about the crystal structures, how to study about the various important characteristics of crystal structure. But as of the Miller indices are considered, it is used for localizing the crystal directions. So now we just go on to the topic. First, let us see what is meant by a Miller indices, how to find the Miller indices. So it's a quite simple procedure and an interesting procedure too, and how to find the separation between the lattice planes. So as of now we have studied about what is a lattice point, etc. Now we go on to a specialized topic called as the lattice planes. What are Miller indices? Now in this diagram we can see that there are a lot of points, so which we specify as the lattice points. Joining these lattice points, there are certain lines which is being drawn in 3 dimension. We call this as an lattice plane. If you want to find the distance between this lattice plane, this Miller indices comes into help. What is this Miller indices? So this Miller indices normally is being specified by a 3 important integer h, k, l, which is being represented within a parenthesis without any special characteristics. So these are the array of points which is used for the designations of plane inner crystals. Now, so this Miller indices we define as set of 3 integers which are the reciprocal of the intercept made by the plane on the crystallographic axis. So these are the set of 3 possible integers which is represented as h, k, l within parenthesis without any special characteristics, and it is used as an identification or used to designate a plane in a crystals, and it is being made by the reciprocal of the intercept made by the plane on the crystallographic axis. What is the procedure to find this Miller indices? If you want to find a Miller indices, a set of 3 integers, the first and foremost thing is that we have to find what is an intercept made by the plane along the 3 axes. As we all know this, x, y, z, which we call it as an coordination axis, are called as the crystallographic axis, and this has to be represented in terms of the lattice constants a, b and c. So this is the first step in finding the Miller indices. After finding the intercepts, we have to find the reciprocal of these numbers. After finding the reciprocal, we have to just find the LCD, that is the least common denominator, and we have to multiply each and every reciprocal with that LCD. And the number what we are getting is the Miller indices, which has to be represented in terms of h, k, l within the parenthesis, so which is used for the designation of a plane. Now let us see an illustration of how we are going to find the Miller indices for a plane that is being given. This is a plane in a crystal. These are x, y and z, and the intercept made on this crystallographic axis are represented as a, b and c with 2 units along x axis, 3 units along y axis and 2 units along z axis. So that means the intercept is going to be 2, 3, 2. So now we have found what are the intercept. After finding this intercept, we have to find the reciprocal, that is 1 by 2, 1 by 3 and 1 by 2. Now we have to find the least common denominator, that is 6, and multiply each and every reciprocal with 6. So the number what we are getting is 3, 2, 3, which has to be written within parenthesis, which is the Miller indices for the plane given. So once again we just go for this illustration. First we are finding the intercept for this plane in a crystal, which is 2, 3 and 2. Find the reciprocal of that, After finding the reciprocal, find what is LCD, and after that you just write all the three numbers within a parenthesis without any special characters. That is going to be the Miller indices for the given plane. And from the Miller indices, it's quite simple to find what are the intercepts. So it is just in the other way go. So we have to find what are the Miller indices, find the reciprocal of the Miller indices, find the LCD, and what you are getting is going to be the intercept. So in both the forms, we will be able to find what are the intercept or what are the Miller indices. But we have to be very careful and ensure that the intercepts can be written with a separation of special characters, whereas the Miller indices should be just mentioned within parentheses without any special characters. That means a comma or a colon or a full stop or a hyphen, etc. Now, what is an important feature? So, as for the numbers, numerical values are given, you will be able to understand about the Miller indices. But once a plane is given and if we ask what the plane denotes, so for that we must know what are the important features of this Miller indices. In order to understand these important features, first let us consider a plane, so which we mention as 1, 0, 0 plane. So here from this we can know that h is equal to 1, k is equal to 0, l is equal to 0. This is a Miller indices for this plane. But how we have drawn this plane? And here you can see that this cubical structure, one of the face is being blackened. What does it signify? What does it mean? Actually, by seeing this Miller indices, as I show that when you find the reciprocal of this, so it is 1 by 1, comma 1 by 0, comma 1 by 0. That means 1, comma infinity, comma infinity. That means this particular plane falls on one axis and it is parallel to other two axes. That is what? So whenever a plane is parallel to a particular crystallographic axis, we say that the intercept made by the plane on the particular crystallographic axis is going to be infinity. The same here. So you can see that it falls only on x-axis and it is parallel to y-axis and z-axis. So which is represented as 1, 0, 0. So how to draw with this Miller indices plane? First we have to find the intercept. How to find the intercepts? First we are taking the Miller indices, find the reciprocal of the Miller indices, multiply with LCD, and what we are getting is the intercept of this, and plot it and we get the plane. So this is the first important feature. So any plane parallel to the crystallographic axis, that means at a particular axis its intercept is going to be infinity. So now for the particular graph, that is particular plane that what we have considered, we can see that 1, 0, 0 is going to be the Miller indices. As I told, the planes, the intercept is going to be 1 by 1, comma 1 by infinity and 1 by infinity, so which gives you 1, 0, 0. So in the other way, when you just go for the other way, we will be getting as 1, comma infinity, comma infinity. So these are the intercepts that is being made. That's again important feature. Here it's only a ratio which is going to be an important, and it's not going to be the numerical value what we are going to specify within parentheses. For example, here I have specified two planes 6, 2, 2 and 3, 1, 1. Both are the same planes. It is only the ratio what we are going to consider, and it is not going to be what is known as the numerical values what we are putting within the parentheses. And normally if you are having, normally we have a question that when the plane is going to fall onto a negative axis, how we are going to specify. So this is an additional information, and here you can see that when the Miller indices is going to be negative, it is being specified with a bar on the top. Okay, so which specifies that a plane is particularly on the negative axis. So it can be on negative x-axis, negative y-axis, negative z-axis, which is represented by a bar over a numerical value of the Miller indices. And these are some of the important planes that we consider normally, and in this session I will be just teaching you how to draw these planes. Okay, so it's not mere picturization, so we can just draw and we can practice how we are going to learn about drawing these planes. And here you can see that this plane, this is your crystallographic axis x, and along x-axis the plane is falling and it is parallel to y-axis and z-axis. So its Miller indices is going to be 1, 0, 0. So what we have seen in our important feature. Thus again plane, here you can see that it's 1, 1, 0 plane. That means this particular plane is parallel to z-axis and the plane falls onto x-axis and y-axis. And this is a triple one plane. There is 1, 1, 1 plane in which it is falls onto all the three axes and which gets you a triangular shape. So this is a same ratio as that of 6, 6, 6, 3, 3, 3, minus 1, minus 1, minus 1. In all the three cases, you will be getting the same plane. So it's not a number what we are going to consider within a parenthesis. It's going to be specifically on the ratio of these numbers what we are going to consider as a Miller indices. So in the crystal, it is very, very essential and it is very important to indicate the direction inside the crystal. So how the crystal goes about. And in order to understand this in general, we can represent the direction of the lattice point. So which is very useful in calculating what is known as the distance between the planes what we are going to consider. So which we call it as a D spacing. And generally we are specifying D is equal to A by root of h square plus k square plus L square, which gives a relation between a lattice parameters and the Miller indices. So the separation between the lattice planes, that is our next topic what we are going to see. And in order to understand this, we can consider in two different cases, a distance between origin and any of the lattice planes or distance between the two planes themselves. So whatever may be the planes what we are going to consider, whether it is from origin or between two planes, we can see that the interplanar distance remains the same. That is what we are going to prove in this mathematical derivation. We are considering a cubical lattice. Inside a cubical lattice, there is a triangular lattice which is under consideration. Now our problem is to find the separation between the lattice plane, that is a separation between this triangular plane and the cubical lattice, that is between the origin and the triangular plane. In order to derive this expression, that is a distance between origin and this triangular plane, let us consider the spacing between this two plane as D, so which we call it as the interplanar spacing. Here we are going to project this crystallographic axis, that is x-axis, y-axis and z-axis, and the triangular plane in order to solve this problem quite easy. Let alpha dash, beta dash, gamma dash are the angle subtended by the crystallographic axis with this normal. That means ON with OX is alpha dash, ON with OY is beta dash, ON with OZ as gamma dash, and A, B and C are the intercept made by this triangular plane on this crystallographic axis. In order to solve this, we are going to make use of a direction cosine law, which is cos square alpha dash plus cos square beta dash plus cos square gamma dash is equal to 1. From this diagram, we can understand what is cos alpha dash, what is cos beta dash and what is cos gamma dash. So here cos alpha dash is going to be adjacent by hypotenuse, that is it is going to be ON divided by OX. Cos beta dash is going to be once again ON divided by OY, and cos gamma dash is going to be ON divided by OZ. So this is between the origin and the triangular plane what we are talking about. It can also be solved with a two triangular plane under consideration. It goes as the same procedure, but here we are going to see about from the origin to the first triangular plane and from the origin to the second triangular plane, and from that we can find what is the distance between both the triangular planes. Here we can see that from the origin, the first triangular plane is at a distance of D1. Then from the origin to the second triangular plane, the distance is going to be d2. If you want to find what is the distance between M and N, it is going to be d2 minus d1. So that is what we are going to consider here. Here the intercept, as we have seen, OA, OB, OC are going to be the intercept. Normally we know that there is a relation between the intercept and the Miller indices. So which are the reciprocal? The intercepts are the reciprocal of Miller indices, or Miller indices are the reciprocal of the intercept. And since the edge length is considered to be A, we are representing the intercept as OA is equal to A by H, OB is equal to A by K, and OC is equal to A by L, such that A is equal to B is equal to C as the cubical lattice. Now from the figure we have already found what is cos alpha dash, so which is going to be ON we have considered to be D1 divided by intercept made on the crystallographic axis, so it is OA. Cos beta dash is D1 divided by OB, and cos gamma dash is D1 divided by OC. When we use the direction of cosine law, which is cos square alpha dash plus cos square beta dash plus cos square gamma dash is equal to 1. Actually, this alpha dash, beta dash, gamma dash is different from that of a translational angle or interfacial angle what we have seen in our crystal system. Now substituting the value of a cos alpha dash, so which is going to be D1, so which is ON divided by OA is A by H. Likewise D1 K by A, and cos gamma dash is equal to D1 L by A. Substituting that in our cos directional formula, we will be getting D square is equal to A square by H square plus K square plus L square. In other words, D1 is going to be A by root of H square plus K square plus L square. So from the origin to a particular plane under consideration, we have found that the interplanar distance is D is equal to A by root of H square plus K square plus L square. By knowing the value of the edge length and what is the Miller indices, we will be able to identify what is the interplanar distance. In a similar manner, we can go for the next plane from the origin to the second plane. So from the origin to the second plane, which is OM, which is going to be D2, we can find that since it is a value, it is a distance between a two lattice point we are considering to be A. So here it is twice the lattice point, so it is going to be 2A by H, 2A by K and 2A by L. So with the same formulation, we will be getting D2 is equal to 2A divided by root of H square plus K square plus L square. So how we are getting this? Once again we use a directional formula, cos square alpha dash plus cos square beta dash plus cos square gamma dash. So by that we substitute the values for OM, we substitute the value of what is OA dash, what is OB dash and OC dash. We get the value as 2A divided by root of H square plus K square plus L square. So from this we can find what is the distance between the two planes ON and OM. So which is D2 minus D1. So once again we get the same value, A by root of H square plus K square plus L square, which is the same as that of the distance of the plane from the origin. So which shows that if they are equally placed, the lattice points are equally placed and the lattice planes are also equally spaced. So we get the value, which is a very important relation which connects the interplanar spacing, the lattice parameter and then Miller indices. So if one of the parameters is known, we can find the other parameters quite common by knowing the Miller indices as a set of integers which is used to designate a plane in a crystal. So this interplanar spacing, a separation between the lattice plane, is one of an important feature of the Miller indices. With the continuation of it, we will be able to see about the lattice constant, which is a lattice edge length A, and the density. They are being correlated by an important relation which is very useful in a mathematical formulation. So normally this is not only used in a crystal physics as such, even when we are going for a semiconductor device, we will be able to use the same formulation in order to find the density of a particular crystal that is being given. So this is a very important relation which connects a lattice constant A, that is the edge length, and the density of a crystal. So how to start with it? First we consider a cubical lattice. Let its edge length or a lattice constant be A. The density of the crystal is considered to be rho, and since it is a cubical lattice, for our simplicity, for our simplification, we use the volume as A cube. So as we all know that, how we can find the mass? Density is equal to mass by volume. So from that we can find what is the mass of the unit cell, so which is rho A cube. Consider the same crystal. Let the number of atoms per unit cell is represented as n, and the atomic weight of the material is taken to be capital M, and we go for Avogadro's number, which is capital N, and here we are considering per kilomole, so the value comes around to be 6.023 into 10 power 26. So here we are going to consider per kilomole of the substance. So normally in chemistry we use about 10 power 23, but here it is going to be about 10 power 26. So from this we can find what is a mass of each atom. So it is going to be the atomic weight divided by the Avogadro's number, which will give us. So this is for a mass of each atom, but if we want to find for the mass of a unit cell, it is number of atoms per unit cell multiplied with the mass of an atom. So this is same as that of the mass of the unit cell what we have computed. So now we can correlate both the expression. So when we correlate it, we get A cube is equal to m by n into n by rho. So this is a very important relation, so which gives a correlation between the density of the crystal and the lattice edge length. So here n is going to be the number of atoms per unit cell, capital M is going to be the atomic weight or the molecular weight, and n is going to be the Avogadro's number, a constant value, and edge length. So if any of this rho is given, we can find what is A. If A is given, we can find rho. And if it is going to be per unit volume, we take this A cube to be unity. So which is very useful in semiconductor physics in order to find the density of a semiconducting materials that is being given. Let us learn how to draw a Miller indices plane. And here are three simple planes, and given the Miller indices parameters, that is H, K and L. And from the Miller indices, we are about to find the intercepts by which we can draw the plane in a lattice, a simple lattice. First, let us go with the first simple Miller indices plane, 1, 0, 0. First is we have to find the intercept. As we have seen the procedure for the intercept, find the reciprocal of the Miller indices, 1 by 1, comma 1 by 0, comma 1 by 0, which gives the value of 1, comma infinity, comma infinity. That is, this particular plane is parallel to y-axis and z-axis, and it falls onto the x-axis. So how to go about this planar axis? First we draw a cubical lattice, represents the three crystallographic axes as x, y and z. This is a very important factor in drawing the Miller indices plane. Without specifying the crystallographic axis, whatever planes we are drawing, it's wrong. So since the intercepts gives the value 1, comma infinity, that is, it falls onto the x-axis, we are just shading along one face of this cubical lattice. So which gives, so this plane represents 1, 0, 0. Similarly, we go for the next simple Miller indices plane, it's 0, 1, 0, same procedure is being followed. First we find the intercept made by the plane on the crystallographic axis, it's infinity, comma 1, comma infinity. And here we know that this plane is parallel to x-axis and z-axis, and it falls onto y-axis. So this is an origin. So from the origin, this is a plane what we are going to consider, so which represents 0, 1, 0 plane. In the same way, we can go for 0, 0, 0 plane or 0, 0, 1 plane. 0, 0, 0 plane represents there is no planar axis on a cubical lattice, and here in 0, 0, 1 plane the intercepts are infinity, infinity, 1, so which shows that the particular plane is going to be parallel to z axis and it's parallel to x axis and y axis, and it is going to be on the z axis, so by which we will be able to draw it. So now we can go for the next plane. One, 1, 0 plane. How to go about this 1, 1, 0 plane? First, a cubical lattice is being drawn. Three crystallographic axes is being represented as x, y and z. Now go for the intercept. So the intercept is going to be 1, 1, infinity. So which shows that the plane what we are going to draw is parallel to z axis. So how to go about this? So it's an easy way to draw this plane. Along x axis, you just mark a point from the origin. Along y axis, you mark another point. Now join this with a perforated line. Now it is just a line, it is not a plane. Now what we have to do is that, you can see that how to remember this, it is a diagonal to the back face of this cubical lattice. Similarly, parallel to this line, we are going to draw another line which is on the front face of the cube. So that means we have to place a point here and place a point here. Now you just draw a perforated line. Now you shade this portion. This gives you 1, 1, 0 plane. It's quite simple. First we are drawing a crystallographic axis, x axis, y axis, z axis. Then we are finding the intercepts 1, 1, infinity. Along x axis you put a point, along y axis you put a point, just join a perforated line. And how to remember this? It is just a diagonal at the back face of the cube. Similarly, you draw a diagonal along the front face. Just draw it and shade that portion of the plane which gives you 1, 1, 0 plane. Similarly, in order to recapitulate whether you have understood, we just go for another plane 1, 1, 0, 1 plane. So once again, how to go about? First we draw a cubical lattice. Then mention the crystallographic axis x, y, z. Then find what are the intercepts made by this plane on this crystallographic axis. So it's 1, infinity, 1. That means the particular plane what we are going to draw is parallel to y axis. Exactly. So now how we go about is, first along x axis we just put a point, along z axis we put a point. Now we are going to join those points with the perforated line. And here for our easy understanding, now this is going to be the diagonal along the bottom face of the cube. Now what we have to do? We have to just draw a diagonal along the top face. Now shade the portion in between this perforated line. So which gives us 1, 0, 1 plane. So it's quite simple. So practice makes the man perfect. So when we are using a different Miller indices plane, we can just practice with a different Miller indices and find what is the intercept and draw these planes.